Okay, so we are all set now. Let us start now. Okay, so as I've already announced that I'm taking the class today, and then Professor Sora will take the class on coming Thursday, Monday, Tuesday, and then on Thursday, on next week Thursday onwards, we will start as normal. Okay, so in the last class, what we have discussed, we have started about combustion in SI engine. Okay, and with the help of the P theta diagram, we try to see that the whole region of the P theta or the combustion region of the P theta can be divided into the three different areas. One is called ignition lag, that is A to B. So how we can define the ignition lag? That it is the time difference between the instant of a spark and the instant of a start of the combustion. The start of the combustion is a very tricky things. It's really very difficult to find it out that where is the start of the combustion. As from this graph, we can say that whenever the firing P theta is deviating from the motoring pressure curve, then we can say that is the start of the combustion. That's the way the start of the combustion has been defined at this in this picture or in this graph. But there might be possible that even if the combustion is going on with very slow rate, and but that part is not contributing as we can notice in the pressure rise. So that is also possible. So that's why I'm saying that defining the start of the combustion is its exact start of the combustion is a bit difficult. So in what normally it is acceptable among the IC engine community, that we need to find it out that mass burn fraction. Okay, and then some people defines the 5% mass burn fraction will be considered as the start of the combustion. Some people also can take 10% mass burn fraction will be considered as the start of the combustion. So whenever you are defining the start of the combustion, then the criteria you have to also define that in this explanation or in these discussions, we have taken a 5% or 10% of mass burn fraction as considered as the start of the combustion, or the deviation of the firing pressure from the motoring pressure has been considered as the start of the combustions. So you have to define it that which parameter you have taken as the start of the combustion, and that is the acceptable universal aspect acceptable among the research community or in the academia of the IC engine. So A is the spark timing, and then B is defining as the start of the combustion, and AB is the ignition lag. So we discussed that this ignition lag, we need to reduce the ignition lag as small as possible. Okay, and to do it, but IC engine, or particularly in the combustion, uh, reducing or increasing or decreasing one parameter is not so simple, because it is not the independent parameter that we can play on it. With that, only the ignition lag is going to be affected, because it has connected with so many other parameters. So if you want to change the ignition lag period, it may affect the other parameters. So changing parameter, one parameter, if we have to take care about the other parameters also, because other parameters may change. Some may be changed in the positive directions, or some may change in the negative directions. So we have to be optimized. What I'm trying to say, that when you are changing the one parameter, you have to be very careful in looking at its effect on the another parameter, and then you have to take it into the whole domain. You have to take it into the consideration. So one region we have defined as the ignition lag, another B2C, where the after the combustions the flame is going to be propagated across the combustion chamber, and it will consume the unburnt mixture. And so the B2C is defined as the flame propagation of flame. This region is very important, because if the flame speed is too high, then the rate of the pressure rise will be very steep. If the flame speed is very slow, then the rate of the pressure rise will be very low, and then the peak pressure will be extended in the later part of the expansion stroke. So the propagation of the flame is very important. Then once the peak pressure will reach at its maximum value, then at that point it is considered as the most of the combustion, most of the flame has reached or has consumed almost all the unburnt mixtures. But still the combustion will go on in the somewhere in the combustion chamber because of the different regions. And then but its effect on the contributing or the power output is not too much, but it is going to affect the emissions very. So in the intermediate side, again the point D, again the way is very typical to change the to what is called deciding the B point start of the combustion is very tricky thing. The similarly the point D, where we are saying that the end of the combustion is also is really very difficult things. So the end of combustion is also we have to define it, and it is considered that if the mass burn fraction, if the 90% of the mass burn fraction has been consumed, okay, then it will consider as that it is the end of the combustion. So when that's the another acceptance by which through which we can define the start of the combustion or the end of the combustion. So the stage of the combustion, that is a very typical curve of the P theta in the SI engine combustion. Obviously, this P theta is going to be changed once you change the operating condition of the engine, change the engine speed, or change the load on the engine. The P theta nature is going to be changed. Or you change the air fuel ratio, or change the spark timing, whatever, or it is going to affect the P theta diagram. Okay. So mainly for our discussions, it's really very important to know that what the ignition lag, flame propagation after burning or end of the combustion. That part we have already discussed in the last class. So now let us come back, and then we just started one thing in the last class with just the little bit introduction, that in the beginning of our class in the semester we have discussed that about the compression ratio of the SI engine and the CI engine. And then with our discussion, okay, in fact you people have suggested or given the answer, and that the compression ratio of the SI engine is lower than the compression ratio of the diesel engine. And the maximum compression ratio or range of the compression ratio of the engine SI engine can vary from 6 or 5 to around maximum 13. We can say 13 is the upper limit. As far as the production level is concerned, I mean the practical condition is concerned, probably it's 12.5 is reasonable to say. Whereas the compression ratio of the diesel engine is very high, and it can vary from 15, 16 to 23, 24, something like that. Now, then after that, that was the beginning of our semester. Then in the middle of the semesters, when we were discussing about the cycle, idle cycle or auto cycle or digital cycle, when we were discussing about the auto cycle, then we find it out that our thermal efficiency is dependent on the compression ratio. And as we increase the compression ratio of SI engine, the thermal efficiency of the engine is also increasing. But before that, we have discussed that there is some limitations on the compression ratio. So that is what today we have to unfold these things, that why the SI engine is restricted to a low compression ratio. What is the reason? What is the technical reason? However, there is no such kind of the reason on the diesel engine, at least. So before that, to understand that why we have restrictions on the compression ratio of SI engine, there is one fuel properties that we need to understand, and that fuel property is called octane number. Octane number, it is a specific fuel properties. For gasoline, there is a octane number. All the fuels related with SI engine, okay, that can be used in the SI engine has an octane number, okay. So can you tell me that or can you give me the example of some of the fuels that can be used in the SI engine? Anyone? One is gasoline, no doubt. Anyway, we are using in our
Kerosene.
Kerosene, okay, very good. Anything else? SI engine fuel. Some of the alternative fuels. Gulshan, are you there? Gulshan? See, the thing is, there are so many, at least one of the another fuel that also we are using very extensively in, at least in India. On that, you can also give the example. Can you give anyone else any name of the fuel apart from the diesel engine? Sorry, apart from the gasoline?
CNG.
CNG. Very good. CNG.
The propane.
Propane, yes, because LPG we use it. Yeah, so
Yes, sir.
yes, yeah, that's really very good. Very good. That's I believe that you know all the things. Only things you don't speak. You speak only when I call a specific name. But anyway, that's really very important that all of you know that all these things. Okay, so what I'm trying to say that all the fuel or octane number is a fuel properties. Even though I have not introduced the term that is called NOC. Okay. Sorry, what happened? Even though I have not introduced the term, but right now, take it as this a word NOC. NOC is a kind of the phenomena, okay, that is not good. Right now, let us assume it is not good for the SI engine combustion. And that's a phenomena that we will discuss in the next slides, NOC. So the octane number, what is the octane number? It is the fuel ability. It is the fuel's ability to resist the knock. Okay. Any fuel that has a higher octane number, it will resist the knock phenomena. Knock is the undesirable combustion phenomena we do not want. And since octane number is the fuel's ability to resist the knock, it means what? We want to have an octane number of the fuel as high as possible, so that that fuel can resist the undesirable phenomena of the combustion. Okay. So gasoline, that what we used, it has the octane number of, in India particularly what we can use, we use, it has an octane number of around 93 to 95, 93 or 95. The maximum value that traditionally we assign the, oh, what happened? We assign the we assign the maximum value of the octane number is defined, is given as 100. So there is a scale on which the maximum value is 100, out of which the gasoline fuel has the value of 93, 95. Obviously, this octane number of the gasoline will be vary from the refinery to refinery, or it also depends upon the crude oil. But we can say in general, that's why I'm saying in India, we use the fuel that has the octane number of around 93. And it is ability. So suppose a fuel that has the octane number of 70, and there's a fuel B that has the octane number of 90. So obviously the fuel B will be more suitable for the SI engine, at least from the knock resistance point of view. Obviously, some other parameters is also going to define the suitability of the any fuel for a SI or CI engine. But as far as the octane number is concerned, a fuel that has the higher octane number will be more suitable for the SI engine from the knock resistance point of view. Now, how we can determine it? That is also very important things. Let us suppose we have a gasoline itself, okay, and we want to determine the octane number of the fuel, gasoline. How we are going to do that? Or there is any unknown fuel, we don't know at all. We have developed some fuel that is considered as for the SI engine, and we want to find it out that what is the octane number. Then how we can find it out? So there is a standard procedure, okay, and then we find it out that what is the octane number. But right now we are not going into the octane number. How to determine the octane number, I will come back after the discussions of the next slide, because to determine the octane number of the fuel, I need to explain the next slide first. Here I have just trying to clear you that octane number is the fuel's properties, and it is its ability to resist the knock. Now the question is, what is knock? That we need to understand, and that is the undesirable, we can say it is an undesirable combustion phenomena. First of all, that line is very important, that knock is undesirable combustion phenomena, or we can say Hello, am I audible?
Yes, sir.
There is a power fluctuations in the lab, and because of that, the internet was disturbed. Okay, that's not good. Okay, let me say once again then. No? Oh, recording is still going on. That is fine. Yes. So we are discussing about, So we are discussing about what is the normal combustion or abnormal combustion. So how we have discussed about the SI engine combustion, that during the intake stroke or before the uh, piston reach at the top dead center from the previous cycle, the intake valve will be open. Okay, and what will happen? The fresh air and fuel, it is a mixture of air and the fuel, will come into the combustion chamber during the intake stroke. Then piston will reach at the bottom dead center, and then it will again start the next stroke, that is compression stroke.
Excuse me, sir.
Yeah.
Sir, your screen is not visible.
Oh, really? Let me check it. Is it true for everyone?
Yes, sir, we can see it.
Yes,
Yes,
sir.
sir.
Okay, let me share once again. Is it shared now?
No, sir.
Okay, let me log out and I'm logging once again. Just be here. Let me shut down properly and then